So first of all, to show the problems that we have with using Gaussian functions and why we can't just use them straight up is this figure from your textbook. So we have in the solid line, we have an STO, a Slater type orbital, and this is for a 1s electron, right? And so we're just looking at the radial part of the function, and so right, we're ignoring the angular part because that's the same between the Gaussian and the Slater type orbitals. And so the Slater type orbital is close to the original hydrogen atom wave functions that we found in chapter 6, and we see this this behavior here where it comes down in negative exponential. The Gaussian function, on the other hand, has this curvature, and especially near the nucleus, which is where a lot of the probability distribution for the electron is, we have a very big disagreement here between the Slater type orbital and using a Gaussian type orbital of the kind we just showed. And it's because of the Gaussian part of it. You're right, e to the minus alpha x squared just has this behavior where it flattens out right at the value of 0 for r, and that should be alpha r squared. Right, and so to overcome this, we'd really like to use Gaussian functions. They are much more computationally cheap to work with. It's much easier to compute all the integrals you need to compute to find energies and wave functions and whatnot. And so we'd like to take our Slater type orbital and represent it with Gaussian functions. And so the solution is to use multiple Gaussian functions to represent our Slater type orbitals. They're that much, even using multiple Gaussian functions is still cheaper computationally than trying to use Slater type orbitals directly. And so essentially what we do, give myself some space to write this, is we have a linear combination of our Gaussian functions, G and Lm, to represent our Slater type orbital. So we might have something that looks like that. So one of the common ones is what's known as this STO-3G, uses 3 Gaussian functions to represent one Slater type orbital. And so we get a sum from I equals 1 to 3 of 3 different coefficients here, d1si, and we have 3 different 1s Gaussian function type orbitals that depend on r and alpha, different alpha values for the different Gaussian functions that we're using. And so what this looks like in practice, if we go down to the second image from your textbook down here, is we get closer and closer as we add more Gaussian functions to the actual Slater type orbital. All right, so this line here represents just one Gaussian function. If we add a second one, we get a little bit closer to the actual Slater type orbital behavior. And as we add 3, we get pretty close. There's still a pretty big discrepancy here, but it's much better, right? And we see that aside from this part, it basically agrees for all the rest of the curve. And so this is sort of the initial way that we can use Gaussian functions to represent these Slater type orbitals and represent our electrons in our computational chemistry calculations. And so what we would do from this point, if we wanted to use this in calculations for a molecule, is that we would use symmetry adapted linear combinations of these atomic orbitals that are represented by these STO-3G functions.